For today's Institute Colloquium. Our speaker is Professor Peter Sarnak from the Institute of Advanced Study, Princeton. And this is an Institute Colloquium co-hosted by the Infosys Science Foundation. Professor Sarnak is visiting India as a guest of the Infosys Science Foundation. And now to introduce the speaker, I request Professor Deependra Prasad.
Both are needed?
Both are needed.
Okay. All right. Very good to see so many people have come to hear this lecture. Any organizer is always happy when the lecture is taken seriously and people come. So it is my pleasant duty here to say a few words about the speaker today, Professor Peter Sarnak, who holds a joint appointment at Princeton University and at the Institute for Advanced Study, who has come to India as the chief guest of Infosys Science Foundation. As many of you might know, Infosys has instituted these very distinguished awards given for all sciences, and he will be the chief guest for the awards this year. All right, so to say a few words about Peter Sarnak. Yesterday I said a few words, but I saved a few words, and maybe there will be a few words which may be repetition. So Peter Sarnak was born in Johannesburg, South Africa. So he is South African by birth. He did his PhD at Stanford University under the guidance of Paul Cohen, who many of us would know was one of the great logicians and who got a Fields Medal. But Peter Sarnak did not do logic. I guess at that point, Paul Cohen was interested in proving the Riemann hypothesis, and I think that is what has got Peter Sarnak started on that path. So he finished his PhD in 1980-81 from Stanford, and after some short postdoctoral appointments, he came back to Stanford and was there rising up the ladder to become a professor, and was there for a few years till moving to Princeton University in 1991. So he has been in Princeton since 1991. He has been one of the most influential mathematicians of our times. One can gauge the influence one has primarily through one's own research, which he has done in abundance, but also through sitting on various committees. And he has been on, I imagine, all important committees in mathematics and on all important journals in mathematics. So I think he has been an editor of a lot of important journals, and through that one can in fact change the course of mathematics, more or less. I mentioned yesterday that he has had 57 students and 75 collaborators, and the two sets are almost disjoint. So he has had amazing influence on mathematics. Today's lecture is on Ramanujan graphs. This is a topic on which he has made very substantial contribution over the years. Ramanujan conjecture is something which, we all Indian feels that, it is something relates to us and so on. But that particular one which relates to us has been proven, but there are many forms of the Ramanujan conjecture, and some of the best results on Ramanujan conjecture are due to Peter Sarnak. Today he will speak about Ramanujan graphs, a topic on which he made contributions early on in his career, and that was a paper that he wrote with Lubotsky and Ralph Philipp. and that is one of the most cited papers in mathematics, and that paper has made the three authors a household name in the computer science community. So I guess a lot of computer scientists are here because they know Peter Sarnak as much as we do. So all right, to say a few more words, in general, Peter Sarnak brings together ergodic and L function methods to questions about Diophantine equations. You know, Diophantine equations are like Fermat's last theorem, and one needs to solve them, and one doesn't know where to begin and where to end. Sarnak has this unique ability to bring methods from different parts of mathematics on such questions. And it's also a topic of much interest to Indian community. I think people in this audience have also made important contributions of bringing ergodic theory methods to questions in Diophantine equations. He has brought number theory, analysis, dynamics, geometry, and spectral theory together, leaving a large impact on all of mathematics. It's a great honor and great pleasure to have Peter Sarnak give this lecture.
Thank you. Thank you, Dipendra, for very kind, I don't know if it's accurate, but very kind introduction. I appreciate it. It's a great pleasure for me to be here to give this university or institute-wide colloquium. And I've chosen the topic, Ramanujan, makes a lot of sense. But I'm going to tell a story, it's partly historical, of the impact of the Ramanujan conjectures on the theory of expanders, which are central in parts of computer science. And then in the second half, I'll tell you how the computer science side of it, the expander side, has been impacting number theory. So when you have something working in one way, usually it works the other way, and both fields are benefit greatly. And that's certainly the case here, though the other direction was much slower. At first, the number theory was very useful for computer scientists, but that has changed. So the topic is interdisciplinary. There's one slide that will be advanced, and you can just ignore it. But otherwise, everything should be quite elementary, I hope. All right, so let's start. I can use this thing, which is probably better. Which I don't know where I should stand. Is there an optimal place to stand?
Maybe you want to stand outside so that you are a little distance.
Okay, I'll walk up and down here. All right, so Ramanujan graphs, the very first line is the most important line. They are graphs. Graphs are these things that you see over there, edges and points. So you could imagine those being useful in a lot of combinatorics and in computer science. Graphs which are very highly connected and at the same time very sparse. So that's a tension. If you connect everybody up to everybody else, then you're going to be highly connected. Everybody's connected to everybody else, but you're not sparse. So the question of what I mean by sparse and highly connected is going to be defined in a minute. But highly connected and sparse is what makes them so useful in communication networks, in theoretical computer science, in de-randomization. I'm not going to talk much about the computer science. I'm just going to make the definition of an expander and then explain that the Ramanujan graph is the absolutely optimal object you can construct. So here are examples of Ramanujan graphs. It turns out that if you make a small graph that's regular, like here, these are three regular graphs, meaning that each vertex has exactly three edges coming out of it, like that K4. That's the smallest three regular graph. And then K33 is the next one, and so on. These small graphs, and the football's my favorite, the buckyball, that's, if you look at the way a football's made, it's cut in such a way that it's a three regular graph with pentagons and hexagons. These are all Ramanujan graphs. I'm going to tell you a story later that will make clear why that's not surprising. Small graphs should be certainly Ramanujan. The interest of making a highly connected sparse graph, which is what we're going to try to do, is, well, I will just tell you how we do it, is that you must have a lot of vertices and few edges. So it's only when you make many vertices that it becomes much, much harder to construct. So there's this paper that Dipendra mentioned. These are LPS graphs. I'm going to actually give you the definition because I want to show you how explicit they are. One of the reasons this was quite a hit, we never realized it would be, was that we gave a completely explicit description so everybody could use it without having to understand how it's proved, which uses all of Grothendieck's work and quite advanced math. But that it works, you can check on a computer, and it's a theorem. It always works. So these are examples of 3 regular graphs, all of which are Ramanujan. So they're highly connected and sparse. And as I said, the tension of being highly connected and sparse is what makes them so useful in applications, especially in computer science. There's a beautiful paper in the Bulletin of the AMS 2006, which is 100 pages, about expanders in computer science and how they're used. I'm going to define an expander. And I urge you to look at that paper. If according to Vigdison, if he were to write a follow-up to that, it would be another 300 pages. That's how useful it's become. So he and I joke that expanders should be taught in high school. I'm going to tell you what they are in a second. And probably here they are. I don't know. All right. So I'm going to make the graph sparse with a lot of vertices. So one way to make it sparse is to make sure that each guy is connected to only few guys. And to make it nice and mathematical and symmetric, I'll assume that each guy is connected to D guys, where D is greater or equal to 3. You'll see in a minute why I want D greater or equal to 3, but D is fixed. So 3 regular would be the first and most interesting case. At my 70th birthday, I'm an old guy. 6 months ago, I was already 70, I'm now 71. Dan Spielman, a well-known computer scientist, gave a lecture, the first lecture at this conference, and said that Ramanujan graphs were a gift to computer science. Well, he's very generous, and I'm going to explain roughly what they are and what he said. But my aim in this lecture is to say expanders were a gift to number theory. That's the other side of the coin. All right, so I'm sticking to D regular graphs. I will always denote the number of vertices by n, and n is going to go to infinity, and D is fixed. So that makes sure they're sparse. All right, here's something from differential geometry that comes from the Laplacian on manifolds if you're doing differential spectral geometry, for example. It's an invariant defined by Chiga in the differential geometric world, which is easily adapted in this combinatorial world. And it's given any graph x, the Chiga constant hx is the minimum of the following. So it looks like it's very hard to calculate, and it is very hard to calculate. But we'll see it's related to something that we'll be able to use in a minute. So you look at all subsets of the vertices which are non-empty. And what's going to make this an expander graph, I'm about to define an expander, is I look at a subset, F, of the vertices, and I look at all the guys it's joined to. So I look at all the neighbors of the subset F. But F is anything. It's got no structure. It's just any subset. I look at the neighbors of that, and I want the neighbors to be big. Well, if the subset, I want to make sure that if I make the set F to be almost everything, then it's going to be connected to, there's going to be very few neighbors. So what you should do is take the size of the neighbors of F divided by the minimum of the size of F and the size of the complement. And as long as that ratio is bounded, that's the definition. And you go over all sets F. I'll give you a picture in a second. The boundary of F, delta F, is the guys that F is connected to. So if H is not close to 0 means you can't partition the set into 2 sets, roughly, which have a small boundary. So let me give you an example. If I looked at a 2 regular graph, that's a cycle like this, and if I partitioned F to be roughly half the vertices, so exactly half if it's even, otherwise as close to a half as you could do it, then the number of F would have size n over 2, but the boundary of F is only going to have a size 2. And of the complement is also size 2. So this H will go to 0 because the boundary is very small. The boundary is 2 divided by n over 2 goes to 0. So that is absolutely not an expander. And if you try and make an expander, it's very hard. If you start trying to do formulae and you try to think of it concretely, in fact, it's so unintuitive that you can make it that there were conjectures in mathematics which, once translated and followed up closely enough, conjecture that expanders don't exist. Those are obviously false conjectures because I'm going to tell you about expanders. So a family, to have a family of expanders, is an infinite sequence of graphs. D will be fixed, D regular. I'll make them D regular. That's not so important. You can drop that, but I'm going to put that, for which this Cheeger constant is bounded below uniformly as n goes to infinity. That's the definition of an expander family. And expander families are very highly connected and extremely useful, and that's what the Victorson paper is about, is explaining expander families, expanders and its use in computer science. As I said, it's not clear they exist. It turns out that most of us thought that the first construction of an expander, according to this definition, is due to Tanner, but it was later found by some people who pointed out that there's, in Kolmogorov's collected works, there's a paper of Kolmogorov and Bosdin, who was the editor of the volume, that was never published. And in this paper, Bosdin makes a contribution to Kolmogorov trying to understand how many neurons you could have in a brain if he's got some model of neurons and wires. And he's doing some geometry of the brain, and he wanted to know that his inequality is sharp, and he couldn't prove it was sharp, and Bosdin proved it sharp by essentially constructing an expander. So I think it's correct, I personally think it's correct to say Bosdin is the first to construct these in 67, and they are constructed by showing that the random such graph has this property. So there's no explicit construction, it's very hard to make it explicit. But if you take the graph at random, it's going to be an expander. And that's not so hard to prove once you know it's true. All right, in order to bring in some mathematics that's closer to number theory, I'm going to reinterpret this expander property as a spectral gap for a certain operator on this graph. So let's just take the adjacency matrix. So this is a matrix whose an n by n matrix whose columns and rows are indexed by the vertices. And if you write down the following linear transformation or matrix, A applied to F is a function on the vertices, which is a finite dimensional space. A applied to F at V is the sum over all nearest neighbors W joined to V of F of W. So you see, if I'm D regular and F is constant, I'll get the number D out back. So there's an eigenvalue at D, and all the other eigenvalues, this matrix is symmetric, so the eigenvalues are real. So the biggest eigenvalue is D. And the spectrum is contained between minus D and D. That's very easy to see. And if you've taken a course in complex analysis and you know what the mean value theorem is, the way you prove a mean value theorem for a harmonic function, excuse me, you will see that D is a simple eigenvalue. That's with a constant function, if and only if the graph is connected. So I'm always going to assume my graph is connected. That's certainly, to be highly connected, you better be connected. And this H measures quantitatively how connected you are. And it's also true that minus D is an eigenvalue if and only if X is bipartite. So bipartite means that you can partition the two vertices into two equal sets, that must be even number, and all the edges run from the one set to the other. And then you can see that minus D is an eigenvalue if and only if it's bipartite. And there's a relation, excuse me, between lambda 1 and the Cheeger constant. The Cheeger constant is what you use in expansion. I'm going to give you a computer science lemma in a second. And that is, this was proved by Cheeger and then in Buse in the differential geometric sense setting, and by Alon and Millman and others in the combinatorial setting. And that's the Cheeger constant is related to the smallest, the next to biggest eigenvalue under D. So lambda 1 is the next to biggest eigenvalue. It's less than D. So D minus lambda 1 you see over here. D minus lambda 1, you see D minus lambda 1 there. So if H goes to 0, then D minus lambda 1 has to go to 0. So if you can make a gap between lambda 1 and D, you will control H. So this shows that, at least qualitatively, the spectral gap between the next to biggest eigenvalue And the biggest eigenvalue measures this Cheeger constant, which is a measure of expansion. So let me give you an example of why this is so useful in networks or in combinatorics or in graphs which are expanded. You can prove all sorts of things. Because if you want to compute the number of edges from any set S to any set T, how many edges go between any set S and T, the expected number would be D because it's D regular times S times T divided by N. That would be your expected number of edges. And that quantity is less than or equal to lambda 1 times the square root of the size of S times, this is called the expander mixing lemma. And it's one way that the expansion is used. So if lambda 1 is bounded away from D with a gap, then if S and T are large, you actually learn there always are edges going between S and T. So if you're trying to make a network and you want to go from one point to another point quickly, this will ensure it. If you ask what's the diameter of a graph, which is an expander, the number of vertices will be very large, but the distance between any 2 points is only log of the number of vertices. So there are millions of consequences of this, all assuring you that it's highly connected. So the question of what's the best graphs in the world, and there's a way of measuring that. In the Cheeger constant way, it's not so easy, but in the spectral gap, there's a limit of how big you can make the gap. So this is a theorem of Alon and Bopana. I think Bopana is a computer scientist. And it asserts the following, that lambda 1, the lim inf, so if you take bigger and bigger graphs, lambda 1 can't help itself. It must be greater than or equal to 2 root D minus 1. So if you're looking, there's an eigenvalue D. The lambda 1 is, I want a big gap here. And this theorem says you can't make the gap bigger than this interval here. Lambda 1 will always have to be greater than or equal to. So the best you could ever do is keep it less than or equal to this number. And I'm going to make it symmetric here because of this bipartite versus non-bipartite. So this interval here, which happens to be the spectrum of this, the best expander in the world is the deregular tree, because everything gets pushed out. This is something I should point out. The boundary of a set in Euclidean space, the boundary of a circle of radius r is 2 pi r. And if in Rn, the boundary, the surface area is r to the n minus 1, the volume is r to the n. But in hyperbolic space, the boundary of a circle radius r is e to the r. And so the boundaries of the same size and the area, or the volume, is also e to the r. So the best expander, if you had an infinite object, the tree, would be to take the tree. But that's not, you have to come back on yourself. And the question is, when you come back on yourself, how to do it so that you don't mess up the lambda 1. And that's what's hard, and that's what the random join. So if you come back on yourself randomly, you can make an expander. So this interval is is the smallest interval that you can put all the eigenvalues in. And so the optimal possible expanders from the spectral point of view are ones for which the eigenvalues lie in the interval. And if you're not bipartite, then I want all the eigenvalues except the top one, which is D, to lie in this smaller interval. That's the smallest possible interval they can lie. And if you're bipartite, then there's an eigenvalue of minus D, and then all the other ones should be in the interval. So if you can make these, they're completely optimal. And okay, I won't go into the history of how we got into this, but the basic story is they exist. So that's what is done in my paper with Lubotsky and Phillips. And Mogulis, who was in the Soviet Union at the time, smuggled out a paper when he heard what we'd done, and he was writing a paper which he smuggled out through some complicated way. It got to me, and he was making a similar construction at the same time. So I put both the names down. His was less explicit, but it was based on the same Ramanujan conjectures. So I'm going to tell you why it's called Ramanujan in a second. That's very important, especially here. All right. So these were constructed this way, and I'm going to give you our graphs. They're that simple. But let me tell you what the Ramanujan conjecture is. Ramanujan conjecture, as Ramanujan formulated it in a paper of his in the Cambridge Proceedings of Cambridge Math Society, is, you probably know, Ramanujan was very interested in Q series, in power series expansions, and he could see all sorts of things that no one else could see. So there's this very important function called delta, which is exactly what I wrote over here. It's elementary to define. You don't need to know anything. It's Q times this infinite product, which if you expand out will be the sum m equals 1 to infinity of some coefficients. We call them the Ramanujan coefficients, as he made the first. This function had been around before. It's Q minus 24 times Q squared plus 252 times Q cubed minus 1472 Q to the fourth and so on. They're all interesting numbers. And what Ramanujan looked at these numbers by just doing some calculations with pencil and paper and observed the first thing, that tau of m times n is tau of m times tau of n if m and n are relatively prime. I don't think we needed a Ramanujan to see that, though he was the first to observe it. But the next thing he wrote, that is genius, pure genius. He also wrote, and it's also true, that tau of p is less than or equal to 2p to the 11 over 2 for every prime p. And why you would put 2 and 11 over 2, all of which is absolutely optimal. So that's the Ramanujan conjecture. And that was solved much later by Pierre Deline, colleague of mine. And I couldn't have this slide turned so that you could see his nice face, but you have to turn your head around like this, and you'll see his face. He was knighted, not knighted, in Belgium he was made a count. And they made a stamp, and on the stamp is tau p less than or equal to 2 times p to the 11 over 2. So, and Deline used Grothendieck's machinery, proved the Weil conjectures, all of which were, we don't know any other proof other than those tools. It's one of the highlights of 20th century mathematics. So that's the original Ramanujan conjecture. We use some versions of it, some simpler versions for the graphs. Okay, now I promised that these graphs are very easy to write down. That's one real reason that they picked up like wildfire. So I'll now tell you how to make these graphs. And they're defined by simple formulae, and they are also defined locally, so you can implement them very quickly. There's no reason that you would want anything else besides these, but that's not true. Computer scientists always want more. Well, can you do this and make them also do that? And so that makes sense because they've got some application in mind. But for the Ramanujan graphs, these are perfect. So I take a prime Q, which is large, and I'll assume that it gives remainder 1 when divided by 4. In which case it's elementary. We know that minus 1 has got a square root modulo Q. So you choose I, which you'll call the square root of minus 1, in the arithmetic modulo Q. So I'm doing remainders modulo Q. For those who don't know that, that's like arithmetic. It's a finite set. And there's a minus 1. And now I make 2 by 2 matrices with entries or in this arithmetic. So I make 6 2 by 2 matrices. The first one is the diagonal matrix 1 plus 2i, and 1 minus 2i, and the second one is 1 minus 2i, 1 plus 2i, and then the next one is just that matrix. Very nice one, and then the third one has also got an I in it. That's 6 matrices, which lie in the 2 by 2 matrices with entries in this arithmetic modulo Q. That's called a group. They form a group. Fancy name there, PGL2. It's just 2 by 2 matrices. There's a division by the center, and the other ones are 2 by 2 matrices with determinant 1. So either you're in one case or the other case. And then the theorem is, in either case, in the first case, if you make the following graph, you make the elements in this group as your vertices, and then you join each guy to 6 guys, the 6 guys being these matrices in S, they're these 6 matrices times that's it. You join, you must decide whether to multiply on the right or the left. These matrices then commute. So you multiply G by S, one of these 6, and you join G to G primed. So there's a local definition of who you join, and you're joining 6 guys there. And then the remarkable thing, this is absolutely optimal. These are Ramanujan graphs. And if that's, depending on whether it's PGL2 or PSL2, you get a bipartite or the other one. So they're very easy to construct, and these are, I think, one good reason that and they've been implemented all over. Now, I want to explain why Ramanujan made that conjecture. People don't know this. They just know that conjecture, it's on a stamp, and it's, Deline proved it. In fact, he was interested in Diophantine equations, and I'm going to get back to this because the passage which gives us some insight backwards is where we have equations that we don't understand, but where the expansion, if you can prove it, you don't have the luxury of using algebraic geometry, but maybe computer science ideas actually are useful to us, and that has happened. So the way this is proved is it's very much related to writing a number as a sum of four squares, which is a classical thing in modular forms. Delta is a modular form. And one is looking at the solutions when n is 5 to the L, that's related to the 6, the degree being 6. And you're looking at the solutions modulo Q and trying to understand something very subtle about that. And while Ramanujan does not describe this explicitly, he says it would be useful to know these kind of inequalities. He knew very well why this is a very important number theoretically. So he made that conjecture with much more insight than just to make, I'm just observing these numbers are less than or equal to Q to the 11 over 2. For us, this is critical. This is the case which gives those graphs. All right, this is the slide that is frightening. I want to point this out because there's an input into the proof of the Ramanujan conjecture that's used here, and that is that at some point we're going to put all the zeros of some polynomial on a circle. And I'm going to return to this in another construction of Ramanujan graphs, which uses statistical mechanics and the Li-Yang theorem. So that's why I'm putting this here. So maybe I don't even define this. Let me just say in words, this is, in this field, when you replace the rational numbers by FQT, it's called the function field, there's an analog of the Riemann hypothesis, which was mentioned, which we don't know how to prove, but which can be proved in this setting. And the first cases that were proved are due to André Weil. And he gave a proof of this, and that in a critical moment in the proof that these eigenvalues lie in this tiny interval is the use of the Riemann hypothesis for curves of a finite field. So it's a great theorem, and it's saying the analog, the zeros on a circle rather than on a line because the variable is used slightly differently. And that's a key input, so just remember that the input that puts the spectrum, the eigenvalues to make the biggest gap in that interval is the Riemann hypothesis. If you ask me, what am I using that's most important here besides modular forms, it's this. All right, so I think I said this yesterday probably, but I'll say it when I give lectures now. When I used to lecture on this in the 80s and 90s, I'd say, well, we use number theory and you'll never be able to do this without number theory. But you should never say you can never do something to young people because they will do it unless you have a proof they can't do it. And I had no proof that you can't do this. And in fact, not only is this theorem remarkable, but I'm going to tell you about something that's 1 week old in a minute. So in 2015, an amazing paper appeared by computer scientists, all computer scientists. I guess they were always trying to make their own construction. Spielmann is the guy I mentioned in the beginning. He made a construction of Ramanujan graphs by doing the following. So Bilou and Lineal made the following conjecture. Suppose I want to make an infinite sequence of graphs with that spectral gap. So what they do is they start with one of those small graphs, which are Ramanujan, and then they look at all double covers. So if you have a graph, and a double cover is just another copy of the graph where you join, instead of joining the guy as you are on the same, you're allowed to go up and then do something appropriately so as to get a graph. And they're 2 to the number of edges double covers. And based on numerical evidence, Lineal also, Bilou, and I don't know, they're computer scientists too, they found numerically that it seems that it's always true that any graph, which is Ramanujan, has a double cover, which is Ramanujan. So if that's true, then you can repeatedly double and make an infinite sequence. And that's how they constructed Ramanujan graphs, by proving this conjecture of Bilou and Lineal. And I want to say a few words about this, because the input to this theorem is the Li-Yang theorem from the Ising model in statistical physics. That's one of the ingredients at a critical moment in their proof. So just like we were relying on the Weil proof of the Riemann hypothesis, they are relying on this amazing theorem about some polynomial having all its zeros on a circle. And this Li-Yang theorem is stated for the Ising model, the partition function, that it's always got all its zeros on a circle. But the version that, a variation due to Hellman and Lieb, is that if you take any finite graph and you make the matching polynomial, so you look, a matching is a subset, a matching of size I is a subset of size I with no edges, where the, of the edges where the edges have no common vertices. So you look at all, you try count all the matchings, and you make a polynomial out of that in one variable, which has got a -1 to the I, the number of matchings, lambda to the n minus 2i. That's a polynomial in lambda. And it turns out all the roots of that polynomial are real. Okay, that sounds remarkable. It sounds already like something's like a Riemann hypothesis. And it is, but it's much easier to prove. Once you know something like that's true, and I'll tell you how Yang describes how he was struggling with this and how he proved it. Anyway, from that, it follows easily that if you look at the, so this is statistical physics, you look at all the S's, AS is this double cover. You look at all the double covers, you look at the characteristic polynomial, determinant lambda I minus AS, the expected value, and it gives this mu, this matching polynomial. And from that, you learn that all the roots are in this amazing, remarkable interval, which we're so interested in. So the average over all double covers has got the spectrum in the right place, but that doesn't mean any one of them does. But then they use some very beautiful work, again from statistical physics, about interlacing polynomials to show that there's at least one double cover which is real rooted. And in this way, they construct Ramanujan graphs. Now, there's a beautiful interview with C.N. Yang, the Nobel Prize winner. He's still alive, I think he's 102 or something, in which he's describing this theorem as his favorite theorem in math. Of course, this is he's an amateur mathematician. So he says he was trying to prove that this partition function has all its zeros on the circle. I just wrote out what he wrote. And they decided it must be true. They were at the Institute as members at the time. This is in the 50s. And so we went to Selberg, a numbers theorist, a very distinguished mathematician. We went to Johnny von Neumann. Okay, he's a friendlier guy, apparently, Johnny. And the reason we talked to Selberg was that number theorists have a sort of predilection for roots on the unit circle. And they were trying to prove this partition function had all its roots on the circle. Anyway, he continues how to discuss how he found the proof. And all proofs of the Li-Yang theorem and the theorem that we're quoting here go along this line, and there's something to be learned for young people here. So he's sitting around in December, he says 20th, just before Christmas, he's struggling on this, they've checked numerically and he can't prove it. And then he has a big idea. Instead of making a polynomial in one variable, in each edge you make the variable different. So you make a polynomial in the number of edges variables. And then you have a statement which is much more complicated. But then you can prove it by induction instantly. So the moral of the story is sometimes you're trying to prove something and somebody comes and says, try prove something a little more. And then all of a sudden it becomes easy. You have to carry the right induction step. And all proofs that I know of this theorem and variants on it involve introducing several variables and then specializing the variables to be equal. And the induction does not work if you just have one variable. It works if you have all the variables. And this becomes Li-Yang polynomials, hyperbolic polynomials, Lorentzian polynomials, a very beautiful subject. So this is how he found that, and that was a critical ingredient. But now I want to tell you something that's really exciting. So you might ask, what about the random guy? So this was written before I was coming here, and then I added at the bottom something which, just as I was leaving, became available. I knew maybe a week before that also. But it's now in the archive. This is an amazing paper. But I have a bet with Nogalon, and he says that the random graph is Ramanujan. I say the random graph is certainly not. I'm saying you won't even ever construct it. So never mind explicitly. And the answer is, that's what the new breakthrough is here, that 69% of them are Ramanujan when n goes to infinity. And when n is very small, 100% of them are when you're very small. And then as you start increasing, fewer and fewer become. And it was clear that this number starts to go down if you do numerics, but it was not clear whether it would go down to 0 or not. And usually if it starts going down, I expect to go to 0. But there was some understanding that some students of mine and I did, after which it became clear that we're both wrong. And I was writing this, that we're probably both wrong, because Wang, Mackenzie, and Yao were within a hair's breadth of showing that this lambda 1 behaves like Tracy Woodham, after which you'd get the 69%. And then just at the turn of the year, 24-25, they put on the archive a proof. It's 150 pages. I don't say it's been checked, but these guys are reliable. So the random guy is Ramanujan with probability 69%. So not only do they exist, but not with 100%. So it's a very interesting phenomenon. All right, so that's the history of that. Now I want to part 2, and let me see how much time I have. So I have till what? 6:10? Yes, 6:15. That's okay. So I have like 15 minutes. So I want to explain now how, so that there are many other applications of number theory in computer science. This is just the one that I've been most involved with, so I thought I would just tell the story. And now I want to explain how expanders have been used in understanding Diophantine equations, precisely the way Ramanujan made the conjecture that you want some kind of bound, and I'll explain how you get that, and I'll explain it in terms of expanders. It's the only way that you can. And so you want to prove that some graphs that come out of some construction are expanders, but we don't have the luxury of having Deligne or algebraic geometry to do it. So we have to do it in a much cruder way, much more combinatorial way, and it's been done. And this comes in a setting which looks a bit frightening, but I'm going to give 2 examples of a number theoretic problems where this comes up. But it's very much in the style of Ramanujan. So suppose I have transformations of n dimensions. They're polynomial maps. So they're maps given by polynomials from n dimensions to n dimensions. I'll give you some examples. And the inverse is also a polynomial map. And suppose it takes integers to integers. So I'm going to give you some examples of that. And then I look at the orbit. So I have finitely many such transformations. I let the group generated by these transformations, I'll call it gamma. And I look at this, I take an integral point, and I get a subset of Zn. And I want to understand what numbers I get in the subset from the orbit. Now, there's something that's standard in this kind of world of Diophantine equations, is you look at the smallest subset to contain this orbit, which is defined by polynomial equations. That's called the Zariski closure. So the smallest subset, which is algebraic, given by polynomial equations. This is something you can usually compute easily. And so all these points lie as integer points satisfying some equation. And we have that for free because we have this group acting on there. And if you want to study the Diophantine equation that results from that, then there's a graph which looks exactly like the graph that we constructed from the one I wrote down there, which came from, secretly I told you where it's coming from, the equation x1 squared plus x2 squared plus x3 squared plus x4 squared equals 5 to the L. That's where the action was. Now, I should clarify, the quadratic equations are very special, but they're non-trivial over the integers. Ramanujan was very interested in the quadratic equation. The quadratic equations are directly connected to modular forms in terms of counting, and that's because it's a homogeneous space. If you want to understand a quadratic equation, you have a group. So if you want to understand a sphere, you have the orthogonal group acting on the sphere, moving you around, and you can use that. You can use group theory to understand it. But if you take any other equation, a random equation, you don't have this luxury of having a group to play there. So the part that's connected to the Ramanujan conjectures is very much the equations which are quadratic or ones which come from invariant theory in homogeneous spaces. But I'm interested in cases which we're not, and then you can make a graph. So if X is, you've got this orbit, and then you look at the solutions in arithmetic modulo Q, which is now a finite set. And I had those generators, so I just take the points in this finite set and I join each point to those points, like I did in the other construction. And so I immediately come with 2 questions that are the same, but they are absolutely decisive in doing Diophantine analysis. just like Ramanujan's conjecture is. So the first thing is, are you connected? You should be able to first decide, does this group act on all the points modulo Q to get all the solutions? And then the much more difficult question, are they expanders? And if they are expanders, you are in business to do all sorts of things like produce primes and do sieving and do all the techniques that we have. So this is a situation where if the group gamma that you get here is not coming from a homogeneous situation, maybe it's what I like to call a thin group, then how do we get expansion? And the answer is we do. And that's coming from combinatorics and many such things. All right, so let me give you 2 examples of this, because I've just given you, I don't want to give you some big theory and not really juicy examples. So here's an example that I've studied a lot, and many of my students, and there's a lot, still this is a very active area. So here are 4 linear transformations. They square to 1, they're involutions. So in 4 dimensions, I'm giving you the standard basis E1 to E4, and Rj on Ek is minus 3 Ek plus 2 times the sum, and then for k not j, it's equal to Ek. And the group generated, these are linear transformations, will be a group that preserves this quadratic form called the Descartes quadratic form, which is a quadratic form for which there are orthogonal transformations preserving it. And these transformations preserve that. And just to make a point clear, the group generated by those 4 transformations is contained in all the integral transformations which preserve it. If it were that, we would be doing standard, not standard, but we would be doing number theory a la Ramanujan. But this group may be thin, and in that case, we don't have those tools, and that comes up in this problem. It's a bit skewed. Those are supposed to be circles, not ellipses. So this is called the integral circle packing. If you take 4 circles, in this case, 21, these are the curvatures of the circles, and the other one has got a sign attached to it. So you've got these circles that are mutually tangent. They got curvatures 21, 24, 28, and minus 11. There's a theorem of Apollonius that given 3 mutually tangent circles, there's exactly 2 circles that are tangent to both of them. So in each of these regions here, I can put in a circle and put in a circle. And now it should be surprising to you, but it's true. And it follows because of those transformations I wrote down, that once the first 4 have integer curvatures, all of them have integer curvatures. And so if you ask, what are the numbers that appear in this, what are the integers that appear here? That's an exotic number theoretic problem because the group is thin. And so if I asked, are there infinitely many primes there, or can I solve equations on here? And this expansion property is the decisive tool. So it turns out there are infinitely many primes here. There are infinitely many twin primes. One can prove all sorts of things here. The expansion is one of the main tools.
What are those numbers, 21, 24, 14?
Yeah, those were chosen so that the first 4 are 4 tuples satisfying the Descartes equation, which are integers. Once that's true, then everything after that will be integers because they come by, each of those filling in is one of those R's. So you have to start off with 4 which are integral, and then the rest are integral. By the way, this was discovered by a chemist called Soddy, who won a Nobel Prize in chemistry. And the Apollonian packings are known to mathematicians, but he discovered these are integral. And once 4 of them are integral, all the others are integral. But then the Diophantine geometry of this is very difficult, and it's been solved by proving an expansion. I'll skip the Markov, I don't have time. But here, let me just say that the fact that we have expansion, so the question of whether these things are connected, the question of whether the graph's connected, was solved by Boris Weisfeiler, and was simplified proofs by Norrie, who's at Chicago, and by Larson and Pink. So the connectedness has been understood for a long time. But the fact that they expand is, that's a big theorem in the subject, and that's Bergan, Gumbert, and myself, and many others. And he has a list of people. It's a massive industry to prove that they expanded. So this is a proof of this, an expander, not an optimal expander, where combinatorics and the expansion idea is absolutely critical to understand this number theoretic question. So when Spielman said, I'm giving you a present, you gave us a present, I'm saying, he gave us a present as well, or he, computer science. The expander is something that, I repeat, should be taught in high school. What did I do there? Is that the last one? Yeah, so I think that is the last one. I don't want to go into the technical things, and there's some other Diophantine equations. But the minute you have a group which is not, the situation is not associated with a homogeneous space, then these things might still work, and do work very often. But proving expansion, you can't quote some Ramanujan conjecture that's been proved, or use Weil, or there's no randomness. So let me just make clear, what I do most of my time is trying to show something is behaving like it's random, but it's explicit. So the Riemann hypothesis is exactly a problem of that nature. If you take the Mobius function, which is a function which is the number, parity of the number of prime factors of a number, and you take some mu of n up to x, so it's plus minus 1, plus minus 1. If that cancels to square root x roughly, like a random walk would, that's equivalent to the Riemann hypothesis. But proving something explicit is random is extremely difficult. Interestingly, the de-randomization of proofs and things like that is using these expander graphs to de-randomize, so they are behaving as if they're random. So there's something about an expander which has already got the fact that it's replacement of random. Oh, all right. Maybe I can stop, but I can go back to this Markov. Let me just go back to the Markov. I do have 3 minutes, right?
Yes.
Okay, this is my favorite equation these days. I've been working on it for 20 years. So this is a case, this is a cubic equation invented by Markov to understand things that I explained yesterday in the colloquium. I won't explain that here, but it's a cubic equation. So for many years, I worked on a quadratic equation, and eventually I decided I've got to promote myself to a cubic equation. Now, I want to emphasize something. You mentioned Fermat's last theorem. Fermat's last theorem is a great theorem, but it has no solutions. I'm interested in equations that do have solutions. And the algebra is very good, like automorphic forms were used there shockingly to prove Fermat's last theorem through the work of Frey, which reduced it to some modularity question. In particular, making the n in x to the n plus y to the n equal to z to the n handleable, because when you vary n, that's no longer algebraic. So algebraic geometry has not produced a proof of Fermat, but automorphic forms have. So but there are methods which give finitely many solutions, which are based on algebra, some on analysis. But if you want to produce solutions to an equation without having a formula, then it's very hard. Where are you going to find the solutions? So these are the problems that I'm very interested in, and how you might produce solutions. Now, this particular equation has solutions. If you take the solution 1, 1, 1, you just check it's got a solution, this Markov observes. But then he observes that if you take these nonlinear involutions, R1 is 3x, 2x3 minus x1, and you fix x2 and x3. That takes me from a triple that solves the equation to another triple that solves the equation. You can explain this in many ways. But I have these 3 involutions. So if I just applied the involution and then did it again, I get back to where I started. So I don't get very far. But if I apply R1 and R2, then I get something that has infinite order, and it starts to produce infinitely many solutions. And Markov proved that all solutions to this equation come from 1, 1, 1 by just applying these moves. And so this is a cubic equation where we actually can say something about the solutions. It's very hard, but we can now use this nonlinear action to say something. And this is an example of the type that I gave you at the beginning. And in this case, I knew there was another slide, but it's got to do with the Markov. In this case, the theory of a nonlinear action and making expanders is wide open. And I think this is a very good area to go to prove expansion for nonlinear actions. In the linear thing, this is now a big machine and always have expansion. But in the nonlinear case, we don't know. And the best we have, and we worked very hard for this, Bergan, Gumbert, and myself. Recently, Will Chen added some very beautiful piece of information which allows for a solution of this. using some algebraic geometry and moduli spaces. And that is that these Markov graphs, so the Markov graph is I look at the solutions and I look at their modulo P. And also are they connected? And the theorem is if P is large enough, they are all connected. This is number very large is what we know works right now. Nobody's checked all the way in between. And it looks like all these graphs are expanders. And if you know they're expanders, you can really make much more leeway than just connecting this. So the moral of the story is that at the beginning, we were giving the computer scientists expanders by constructing them using tools from automorphic forms, and especially the solution of the Riemann hypothesis. And now there's no optimal thing here. We just want to prove something is an expander. That's enough for many applications. And this is being done in the linear case and remains completely open. In this case, just the connectedness was very difficult. All right, let me stop there.
We can take a couple of
Yeah.
questions. So we can take a couple of questions, a few questions, yeah.
Yeah.
So is there any connection between the Marcus Spielmann Srivastava construction and your construction based on number theory? In particular, the real rooted polynomials can be understood in terms of Bernoulli's sums of Bernoulli variables. So I was wondering if there's some kind of probabilistic way to understand the finite Riemann hypothesis.
Okay, so this was a dream of the minute Li and Yang proved this theorem, and I didn't quote from this. So there were people who, Polya and people like that, trying to prove the Riemann hypothesis. And the minute these Li and Yang proved this real rootedness or on the circle, people said, this is going to be the door open to the Riemann hypothesis. But the proof actually, the big thing in that theorem, it's proved by induction. It's just that you have to do it the right way. It's not proved in any other. So it's very easy once you have the statement in several variables, exactly what Yang was saying. Its connection to the Riemann hypothesis, Mark Katz in the review, which I didn't quote, says that this paper, he thinks, brings us within a hair's breadth of proving the Riemann hypothesis. Yeah, I don't agree with that at all.
But how about just the first half of my question? I mean, is there any connection between the two constructions?
No. So it's just they both. So I always felt there was no connection at all, but now each of them is leading to a proof of existence of Ramanujan. Yeah. So the proof of Spielmann-Srivastava is not explicit either, because there's only you have to find of all the covers, there's only one. So this random statement is now sort of supersedes this, but it's a fact. It's now true. It's an interesting fact. Yeah. Anyway, people have wondered about this, and there's no connection that any of us know.
Hello. In a graph, one can go from vertex to vertex following a number of edges, and the minimum such would be called the distance between these two.
Yes.
And the maximum of 4 pairs, the size of the diameter of the graph.
Yes.
So how does this diameter
Yes.
go with x?
Yeah. So any Ramanujan graph and any expander already has logarithmic diameter, so it's as small as it can be. And if it's a Ramanujan graph, it's got with a constant, probably, we don't really know the exact diameter. It's off by a factor of 2 maybe, but we pretty much understand these things. Actually, for Ramanujan graphs, we do know, and it's off by the sort of optimal that it could be. So we understand this very well, but there's something that's very nice that exists for Ramanujan graphs that's probably very important for quantum computing. When you do the same thing in another setting of unitary transformations, you can actually navigate. So if I give you 2 points, can I navigate from one point in this graph to another point quickly, the shortest path? That I don't know how to do. I can show that's NP complete to find the shortest path. But if you allow me to go from one point to another and get a path which is 3 times longer than the shortest, then that you can do in polynomial time, and that's a number of people. So these Ramanujan graphs have the friendly feature of actually not just having a simple formula as to who you join to, but actually if you give me 2 guys and I want to find how to go from the other. And of course, the way you do that is to go back to the equation and you solve the Diophantine equation. And there is a tree underlying all this, which I haven't explained. And once you get to that tree, we do know how to go from A to B on a tree. There's only one path, and you just, but you have to find the point on the tree that you want to run to. So the answer, I think that's very nice, but it's NP complete to actually navigate. So the shortest is a difficult problem. Yeah, but the diameter is as small as it can be, up to a constant. So they have extremal in many ways.
Sir, it may be can listen a little nice, but one thing you said that if P is large enough, then everything is connected. There's nothing is random.
You mean in this theorem?
In
Yeah. M star means not 0, 0, 0. M star means you remove 0, 0, 0, which of course is a fixed point for all those transformations. And then it's a theorem that I go to any solution in the set and any other solution, I can find these R1, R2, I can move from the one to the other. By the way, we actually have to go beyond the Riemann hypothesis to prove this at some point. We have to go into the elementary proof of the Riemann hypothesis for curves, which gives some critical information which allows us to get from one point to another. This is quite an involved.
But sir, the Riemann hypothesis is based on Hyperbolian geometry and but
I haven't told you where the Riemann hypothesis comes in here. It's because this is the proof. Okay, at some point, let me give you a very one-line idea of the proof. We first show there's a big giant component inside here, and then we want to join everybody to the giant component. So when we want to join to the giant component, we have to make sure that we find some local moves, and I want to show that I get closer in some form. And to do that, I have to count some solutions over the finite field, and the Riemann hypothesis, which is usually very powerful for that, is not enough. And we have to go further. And so we have to use elementary proofs, which is something very pleasing. Very pleasing to go beyond.
Just one thing.
Like
you were saying that there is an underlying trigger that connecting. So that is...
No, that's in the other case.
But that was Hyperbolian geometry.
Yeah, that was in the case of the trees. So the trees for the Ramanujan graph, our original Ramanujan graphs involve a tree, and that's because the universal cover of the D regular, say 3 regular, is a tree, and somewhere that comes into the number theory.
Anyone else?
Yeah.
Yeah.
Just a question on the Diophantine equation of interest in the Markov Diophantine equation.
Yes.
So you said that the solutions, all the solutions are generated by
1, 1, 1.
Axiomatic group 1, 1.
Yeah, in this case, yeah.
Yeah, so it is similar to this Pell's equation. Pell's equation also all the groups.
Correct. But in Pell's equation, these things are not connected because it's a cyclic group, and depends on what the order of some element in the multiplicative group is. There's something called the Artin's conjecture, which predicts that for infinitely many primes, something will happen. So this feature this has got a lot in common with the Pell equation, but we can prove things for it that are just not true in the other case. Yeah, so it's a good question, very good question. This is the solutions, I should say this, the solutions to this Markov equation in a big ball only grow like log squared. So they're very sparse. And there's a very beautiful proof of that by Mirzakhani using Teichmuller dynamics. And we use it to do sieving on this. Yeah. So this is kind of a nonlinear version of
the automorphism group of this 3 variable degree 3 equation that you wrote.
Yeah, is it generated by this?
Obvious. I mean that those are automorphisms and they generate the automorphism.
Yeah,
group.
right. So it's very big for a surface. This is as big as the automorphism group of a surface can be. It's
because I think one is used to only thinking about linear automorphisms, and these are non-linear.
They are not linear, absolutely.
And, whether they will be automorphisms is not clear, and
Yeah, it's very
they generate is not clear. So
right. So if you change the equation a tiny bit, I love to get.
okay.
Yeah, so this equation is a cubic that we can say something about. But change the equation, I said this yesterday because this is a way to get people interested. Which numbers are sums of 3 cubes? So there is an obstruction that if you are 4 or 5 modulo 9, you are not, if I remember correctly. Just because if you look modulo 4 and modulo 9. And then it's believed that every other number is a sum of 3 cubes. And then we have no tools. Mordell said this is harder than anything he ever saw because you don't have any tools to do it. Even 33 was not known. People were looking on a computer. And Booker, it even hit some newspapers, found the smallest solution to 33 a sum of 3 cubes. And each number is 17 digits long, the smallest solution. But he's only found 1 or 2, maybe 5 solutions. So we don't have ways of making new solutions from old ones, which is why I said making solutions can be very hard. If there are a tremendous number of solutions, then you might be able to run some Hardy-Littlewood method or something. Yeah. Of course, Ramanujan invented the Hardy-Littlewood method, as Selberg likes to say. Yeah.
Okay, let's thank the speaker again for a fantastic lecture.
I do have a question. Do I pronounce his name correctly, Ramanujan?
Ramanujan, yes.
It's like the A is like less pronounced, basically.
I would
Because
like
a
to.
lot of people say, yeah, I don't want to say what they say, but
I would now like to invite Professor Neela Nataraj to give a memento to the speaker.
Thank you. Well, let me get down here.
So thanks once again. It's my pleasure to give the formal vote of thanks to all the people who made this Institute Colloquium possible. Let me thank the Institute Colloquium Committee and the PRO office, and also CDEEP for the live streaming of the talk, and the Infosys Science Foundation for co-hosting the event, and most importantly, our department office and the excellent staff for making all the internal other arrangements. Thank you all for coming. And there will be high tea outside, please join.